All right, so continue on with our multiple linear regression here, chapter 11. We did, I think, just about everything we might want to debate, well, the basic stuff for our iris data set. Okay, one of the last things we talked about was the overall f-test, testing whether all of the betas are equal to 0, or at least one of them is non-zero, right? Basically at least one of the slopes is non-zero, right? Which meaning at least one of the predictor variables is useful in the model, right? And I don't really care about doing the f-test by hand. I mostly just, you know where to find it in the bottom right-hand corner of the summary. That's where it gives you the p-value, which tests basically whether the model is completely useless, right? Pretty much. We also talking about the coefficient of determination. Okay, there's a formula for it. Don't really care about it so much though. Between 0 and 1, and again, it is the proportion of the variability that is in the response that is explained by the model. Okay. And as I mentioned last time, um, basically the way we interpret these intercept uh, parameters is the same. The only difference is it's conditional on the other variables being included in the model, right, and being held constant. Okay, maybe I should have also emphasized that, right? For every 1 unit increase in, say, x1, we expect y to change by this. Well, I said with the other variables kind of held constant, okay, which implies that they're included in the model, okay? And likewise with the confidence intervals, it's just always, with everything else, held constant, with all the other variables in the model and held constant. Okay, so again, prediction intervals versus confidence intervals, the interpretation is exactly the same. Confidence intervals are for the average value of y. Prediction intervals are predicting a random single observed y, okay? And the only difference is now we have to put in x values for each predictor variable, right? x1, x2, x3, etc. However many x variables we have to, right? We have to know what x value we want that to be in order to make a prediction of the response, right? There would be some, right? This would be something of interest to us, okay? Right? Not just some random thing. There would actually be some x values that would be of interest to us in predicting y. Okay. Um, so now I want to go ahead and do another example. Homework 5. Question number 6. So we're interested in the speed at which a particle travels through a certain type of solution. We have 40 measurements on particle speed, solution viscosity, and concentration of a certain substance within the solution. And we would like to determine if the viscosity or substance concentration seems to affect the speed of the particle. So what it wants us to do is fit a linear regression model with no higher order terms to the data. Okay, higher order terms. We can go ahead and talk about that now. Before we fit it, what does it mean to fit a model with no higher order terms? Okay. So our multiple linear regression model looks like this, right? Beta naught plus beta 1 x1 plus beta 2 x3, etc. What a higher order term would be, okay, is, and you can actually do this in simple linear regression as well. And maybe I'll go ahead and go back to simple linear regression. Okay. Go back to simple linear regression because you can have higher order terms in simple linear regression too. Well, it kind of takes the simple out, but say you have your scatter plot, okay? And in this case, this straight line fits it quite well, okay? And you're basically done. But a lot of times a straight line might not be the right fit. A lot of times it is, but a lot of times it might not be. There are many real life variables and quantities where the relationship between the two variables is more curved, okay? Curvilinear, okay, just curved, fancy word for curved, okay? So let's say you have some curved relationship, right? Just imagine the scattering of points just curving a lot more. So if they did that, then a straight line wouldn't really fit very well, would it, right? Y is equal to beta naught plus beta 1x, trying to fit a straight line through that. It just wouldn't work out so much, okay? And so, well, one thing what you might see if you tried to fit that is you might see that the coefficient of determination, right, the proportion of y explained by x is not very good. But really one thing you might see is when we check the assumptions on our epsilon, right? When we check our assumptions, which we still haven't gotten to. Okay, we're getting there though. Okay, so when you go to check your assumptions, if you try to fit a straight line through a scatter plot that looks curved, usually you'll immediately notice something's wrong. Okay, but one thing I'll say, so a higher order term, let's say you still just got one x and one y. Of course, you always only have one y in what we're talking about. And you have a curved scatter plot. You can clearly see a nice curve in the scattering of points. If that is the case, then one thing that you can do is not just have y is equal to beta naught plus beta 1 times x. Okay, right, this fits a straight line, and of course this straight line is not going to do a good job going through a curved set of points. What you can do is add a higher order term of x squared, right? Squareds are curves, right? So what we could add is plus beta 2 times x squared, okay, x squared. So beta naught plus beta 1x plus beta 2 times x squared. This is a higher order term, okay, higher order term, okay, because it's not the lower order terms or kind of the base terms are just simply the variables themselves, right? However many variables, right? You might have x1, x2, x3, but it would just be each one of those in the model with a beta attached to it, okay? A higher order term would be you could take any one of the variables, in this case we just have one variable, but if you take that predictor variable and you attach some function to it, like squared or log e to the, right, anything, take your favorite function, cubed, anything like that, that is what's called the higher order term, okay? And that would be an example of something in simple linear regression that could account for a curve is adding that squared x higher order term. That would be much more likely to fit a curved scatter plot. As I've said, in this case, a straight line looks like it does perfectly fine. Okay, and in general, when you have a simple model that fits good, right, like in this, I would see absolutely no reason to fit x squared, right? You don't want to add terms if they don't help the model. And of course, one way that we can determine whether, okay, do I need that x squared or not, is by looking at how well the assumptions of the model are satisfied, which again, we still haven't gotten to. But you could also look at the coefficient of determination, right? The proportion of y explained by x, okay? So for example, if I add this, how much more of the variability of y am I going to explain, okay? And if it's not much, then might not be needed. If it's a bunch, then it indicates that it might be needed, okay? Again, we always have to check the assumptions, which we still need to get to, okay? So that's a higher order term. Here's another example. Let's say we have two different predictor variables, okay? We've got x1 and we've got x2, right? This is now a multiple linear regression model. Okay, there are no higher order terms here. This is simply beta times a predictor. Another example of a higher order term is what's called an interaction. So this is called an interaction. What we have is beta 1 times x1 plus beta 2 times x2 plus beta 3, some new regression coefficient, times x1 times x2. Okay, this is just another very common example of a higher order term. What this means is that, say for example, this model, everything is useful, right? We've kind of verified that everything fits well. All of these p-values are low for each beta, right? For beta 1, beta 2, and beta 3. Each one of these p-values is low, right? So everything is great. So what this indicates, if this is needed, is that, okay, this right here says that yes, x1 is related to y, okay, and also x2 is related to y. But what this says is that not only are each of these individually related to y, but somehow their combination, okay, the specific combination that they have is actually important in affecting y. So one thing that you can sometimes see is that maybe for, say, when x1 takes really high values, it changes how much x2 affects y. Okay. Basically, the way these two variables interact with one another, because that's what this term is called, that is an interaction. Okay. That these two variables not only are individually important in predicting y, but together they interact with one another in affecting the response. Okay. So that's another common example of a higher order term. Okay, so we're fitting a linear regression model with no higher order terms to the data. So immediately before I even fit it, what it's going to look like, we've got 40 measurements on particle speed, solution viscosity, and concentration. And we would like to determine if viscosity or substance concentration affect the speed of a particle. Notice there's no x's, there's no y's, but just from this last sentence here, you should immediately be able to tell the speed of a particle is y, viscosity is, say, x1, and substance concentration is x2, because we're trying to see if x1 and x2, right, affect the speed of the particle. Okay, so we have two x's, and so it's a no higher order terms, so our model is going to look like y is equal to beta naught plus beta 1 times x1 plus beta 2 times x2. That is what our model will look like. Okay, so let's see if we can find the particle data. Okay, particle data. Put it on my desktop. Again, it is on Blackboard. Get my Weibull analysis code. Oops. And change my username. Change my data set. All right, 40 observations, speed, particle speed, viscosity, concentration. Okay. So one thing I'll go ahead and do, make my life easier, is attach my data set. And now I can refer to these column labels directly. Okay, instead of having to do my data bracket comma 1 bracket trick. Okay, that type of thing. Okay, so again, I'm trying to fit my multiple linear regression model here relating viscosity and concentration to speed. So I need to call it something. Again, you can call it reg.model, you can call it anything you want. Speed, again, capitalization matters, or whatever, if it's capitalized, caps matters. Speed is equal to viscosity plus, right, just separate them by a plus, concentration. Okay, so read your data in and modify this reg.model. And this is what should fit that model. So let's look at it. So this is my estimated model. So y hat, right, my estimated particle speed is equal to 49 point, I'll be lazy, 8 minus 0.69 times viscosity minus 0.31 times concentration. Okay, there's my estimated model, right? If I've got a viscosity, plug it in, I've got a concentration, plug it in, and once I plug in those two values, right, it spits out, put it with the intercept, and it spits out what I believe the particle speed will be. Okay, let's see. Calculate the coefficient of determination and describe its meaning in the context of the problem. Okay, so to calculate the coefficient of determination, we need our summary function. And here's our multiple r squared. So interpreting it together, viscosity and concentration account for, I'll just say, right, it's 0.4974, right? Account for about 50% of the variability in the speed of a particle. Okay, so together these two variables account for about half of the variability in the particle speed. Okay, meaning it seems like they do, right? It seems based on this, right? They're accounting for half of the variability. That certainly leaves room for improvement, but it does seem like there's a relationship, right? If you just tack in two useless predictors and throw those in there, you know, they probably shouldn't account for much of the variability if there's no relation. So there looks like maybe there's a relation, but maybe not a super strong one, okay? Right, we saw in that other example, in the flower example, that the three predictors accounted for like 97% of the variability. That was a lot, okay? You won't get that all the time. Okay, that's like really, really good. Okay, interpret the estimated regression coefficients, right? The betas, right? The beta hats in the context of the problem. Be specific. Okay, so to get those, what do we need? We need not some. Do we need summary? Oh, is it just interpret the coefficients? What was it? Oh, it is just interpret the coefficients, not a confidence interval. So interpret the coefficients. Okay. So we expect, let's interpret beta naught hat. We expect the speed of a particle to be, right, about 50, right, 49.77, to be 50. And I don't think I included units. Let me just double check here. Okay, yeah, there's no units. So to be 50 units when viscosity and concentration are both 0. So again, maybe that's useful. That actually could be useful in this problem, maybe not, I don't know. Okay, but usually the ones that are more of interest are the intercept or the slope parameters. So beta 1, for every 1 unit increase in x1 is viscosity, right? x1, x2. Viscosity, we expect particle speed to now decrease, right? Beta 1 hat is negative, decrease by 0.69, okay? right? Provided concentration is held fixed, right? So basically, I don't care what the concentration level is, but as long as concentration level is fixed, if I only change the viscosity by 1 unit, then I expect this result. Okay, one more to interpret, beta 2 hat. For every 1 unit increase in beta 2, or sorry, x2 concentration, we expect particle speed to, again, it's still decrease because it's negative, provided x1 viscosity is held fixed. Okay. All right. For every 1 unit. Okay. So that is the interpreted regression coefficients. Okay. So both seem to have a negative relationship. At the 0.01 level of significance, does either variable appear to be helpful in predicting particle speed? Explain. Okay, so alpha is 0.01. And still in this, we can get our answer, okay? So let's take a second, look at that, and think for yourself. Do either one of these predictor variables appear to be useful in predicting particle speed? Okay. Once you're practiced enough on a test question, right, it shouldn't take you any longer than what I just gave you to figure the answer out, right? It's very simple if you've practiced. If you haven't practiced, right, you can spin your wheels all day and not get anywhere. Okay, so first thing we might look at right here, p-value, 0.01 is the level of significance, okay? 0.08 is greater than 0.01. This p-value suggests that beta 1 could be equal to 0, and thus viscosity is not useful. Let's go to concentration. P-value, 0.13. This is greater than alpha, 0.01, suggesting that we again fail to reject the null hypothesis that beta 2 is equal to 0, which suggests that concentration does not appear useful. This suggests that viscosity is not useful. This suggests concentration is not useful. From the last lecture, though, remember I said you can never kick more than a single variable from the model by these p-values. You could only determine if a single predictor had a high p-value, you could determine that it was not useful and kick it from the model. But you can never kick more than one. Now I told you in order to kick more than one, but not all from the model, you would have to use what's called a partial F test, but I didn't cover that. You're right, I would like you to know that. But in order to kick all of them, right, in this case we only have 2, so kicking both of them out would be kicking all of them out. That is what's called the overall F test, and that you can determine from this table still. Right here, right? This p-value is the overall F test p-value, testing whether, in this case, beta 1 is equal to 0 and beta 2 is equal to 0. And right, this is 3 times 10 to the negative 6. This is very small and much less than 0.01. So this says right, which is the null is beta 1 is equal to beta 2 is equal to 0. Both predictors are useless because their slopes, the slope parameters are 0. Because the p-value, right, which is 3 times 10 to the negative 6th. Okay, that looks terrible. Just 3 times 10 to the negative 6th is less than alpha, right, 0.01. We reject the null hypothesis that beta 1 is equal to beta 2 is equal to 0, and we have evidence that, we have evidence that at least one of these slopes is not equal to 0. In other words, we have evidence that at least one predictor variable is useful in the model, right? Because a slope being non-zero means that there's a relationship between that x and y. So this overall f-test determines that we have evidence that one of these is useful. Okay, it doesn't say which one, but it says we have evidence that at least one is useful. Notice that is in direct contrast to the information that we got from these. This says viscosity is not useful. This says concentration is not useful. This says at least one of them is useful. And this is what we have to follow. Okay, this is a common case of where both of these variables are kind of measuring the same thing, right? Just thinking about it. Well, the viscosity, right, kind of how thick the substance is or the liquid is. Well, if you've got the concentration of something in that substance, well, whatever substance that is, the concentration of it is probably what's causing it to be more viscous, right? So the more concentrated it is, the more viscous it is. So both of these are basically measuring the same quantity, right? And how viscous it is related, right? The particle travels slower, right? Negative relationship when it's more viscous. It travels slower when there's a higher concentration. But both of these are just measuring the same thing. Okay, they're measuring how thick the liquid is, pretty much. Okay, so both of them, right? If you include one in the model, right? So if you include viscosity in the model, then concentration doesn't tell you anything else. But if you include concentration in the model, viscosity doesn't tell you anything else. So kind of it tells you that one of the predictors kind of encompasses everything. But the main point is you should not kick both out of the model and declare that neither one of these is useful, okay? Because that is exactly the wrong conclusion. This p-value suggests that we have strong evidence that very low p-value that at least one of these is useful. Okay. Now from here, there's a couple different ways that you could go about it, and part of how you might go about it is looking at how well the models fit, but sometimes you might just want to just leave both of them in the model. Okay. If prediction is what you're after, then you might want to include both of them in the model, just kind of maybe a very broad general type of thing. But if interpretability is what you're after, you'd probably just be better suited including a single one of these variables and kicking the other one out, like, well, this p-value is a little smaller, maybe go ahead, and it seems a little more interpretable too, just going ahead and kicking this out, so that, because right, if say we kicked concentration out and then we had basically viscosity is x and speed is y, then we're down to a simple linear regression model, right? Then we can like look at a graph and do things like that. It's nice and simple. Okay, so depending on the fit, but also depending on whether we want better prediction versus more interpretable, because usually, right, including this other variable might help prediction a little bit. Okay. One of the things that you could do, we'll go ahead and do that, is you could look at, I'll go ahead and call it reg.model 2. Let's look at the simple linear regression of just viscosity and speed. And summary, basically looking, okay, together these explain about 50%. Now I kicked concentration out. If this drops by a bunch, right, then it's telling me, well, maybe that explained. Okay, it dropped a little, right? It went from about 50 to about 46, okay? Now there's still other things like assumptions, checking whether those assumptions on epsilon are right. But if you're really concerned with having a nice simple model, it doesn't look like kicking concentration out affected at least the percent of variability explained in speed by just having this nice model. But notice it is a little bit more to where if all you really care about is being able to predict as accurately as possible, then maybe you're better suited off just keeping both in the model. Okay? All right. So remember, never kick more than one thing out by these p-values, only a single thing. This tells you whether you can kick all of them out, and if you have, say, more than 2 variables, and say 2 or more but not all have high p-values, you would have to do a partial f-test to determine whether multiple variables could be kicked out of the model. Okay? And another thing, let's say that you have lots of variables and there's a couple that have high p-values. You should never just like, okay, I'll kick one of them out. You don't want to do that. You would want to do the partial f-test to determine if you can kick both of them out. Okay. All right. Okay, that's pretty much homework 6. Let's see. Here are the solutions again. You have the solutions, so you can kind of look at everything yourself. But I really wanted to kind of go through the problem so that you can, see exactly what we did. Okay. But you basically have the solutions right here. Okay. So all right, so I think that's most of the stuff besides what we've basically been delaying, which is checking the assumptions. Okay, and I'll save that for next time really, but just to put it fresh in your mind, what are we going to be checking? The 4 assumptions on the error term, right? We had this for simple linear regression, and we have the exact same thing for multiple linear regression. We assume that the expected value of these error terms are 0. We assume that they all have the same variance. We assume that they're independent, and we assume that they're normally distributed. Okay? And next time I think we'll start showing how we could verify that.